Welcome back, everybody, and here we are for Chapter 2.3, Energy and Changes in Energy. Now, energy in general is just the capacity to do work or transfer heat. You bend over and you pick a book up off the floor and you set it on your desk, well, you did work. And actually the definition of work is just the amount of energy by the distance it was traveled. So if you lifted it 1 meter, you did less work than if you lifted it 2 meters, how far it goes. But whenever energy gets converted from one form to another, like converting from chemical energy in your body to the mechanical energy of moving it up onto the desk, either through a physical or a chemical change, no energy can actually be created or destroyed. This is the first law of thermodynamics. You got to know this one. First and second law, very important. Now, you probably have already learned the first law of thermodynamics as the law of conservation of energy. It's really the same thing, but we're going to talk about in the realm of physics. We really refer to it as the first law of thermodynamics. Energy can neither be created nor destroyed, only transferred from one form to another. And this is a pretty important distinction. Now, I've got a fairly simple demo set up. So I have my windmill. And instead of trying to use steam in a steam pot, which is kind of complicated, I'm going to try and generate some through a chemical reaction instead. So I have some hydrogen peroxide in the Florence flask here, and I have some magnesium oxide. Now, this goes pretty quick, so we're going to see if we can get some reaction. Not really enough to spin there we go. Unfortunately, I don't know if you could see the spin wheel pinning because of the energy, but there we go. So here's an aspect of energy being transferred. Now, what I have coming up in here, actually smoking everything up, is just oxygen. The hydrogen peroxide is H2O2, and my dog wandering around in the back. As we all know, H2O is water. Hydrogen peroxide is actually not very stable. It doesn't like to be hydrogen peroxide. It wants to give off that other extra oxygen. So what I get left with is primarily water with some manganese oxide left over because it's just a catalyst and it's putting oxygen up into the room. But through that giving off of the gas or steam, it'll spin my pinwheel. So I didn't create energy. All I did is transfer it through a chemical reaction, but I could use that energy of the steam being pushed up through a small opening and make some work. Spin my pinwheel or spin a turbine. The thing is, we always wind up with lower quality energy than what we started with. Let's look at another fairly simple demonstration, sort of similar. So here I have I didn't think about it, it's going to be green, so with my green screen it might look kind of funny. But I have a pinwheel here, and I'll try and get a little closer to the camera and stay in it, and a classic hair dryer. So if I run the hair dryer, notice so the hair dryer spins my turbine, and if I get enough of it, it causes trying to tap, a little light shows up down here. Now, obviously, this is an incredibly inefficient form. I'm using electricity, so ultimately, really, In Gainesville, they're burning coal at the power plant, creating electricity. I'm using electricity to create mechanical energy to blow wind, and I'm using that wind to turn this turbine so I could get a tiny little LED to light up down at the bottom. Horribly inefficient. So the second law of thermodynamics talks about how energy gets degraded. I can only change it from one form to another, but in all these transfers of forms, something gets lost. Typically, it gets lost as heat into the system. We're burning the coal to create steam to spin a turbine. Well, there's heat loss there. As the turbine spins, friction, I get some heat loss there. We put electricity into the power lines. Well, some of the power lines actually fall out, or doesn't fall out. Some of the electricity bleeds out. Then we get it into here. I'm spinning another turbine. More heat is generated through the hair dryer to do this. So all along the way, I keep getting a lower and lower quality or less usable energy. Ultimately, I'm using 120 watts to turn on something that I can do with about 1.5 watts. Just a very small battery would make this light up, but I had a hard time doing it even using the big hairdryer. So we lose energy along the way. Now, energy comes in many different forms. We have kinetic energy. Kinetic. Make sure you connect that word in your mind with motion. Kinetic energy is the energy of motion, anything moving. A stream flowing down, that's kinetic energy, it's moving. A rock rolling down a hill, kinetic energy. It's also, we talk about in terms of heat or heat transfer. Heat is just the average temperature, the average speed of the molecules moving around. Heat is still movement, so it's kinetic. The molecules are moving around. The faster the molecules move, the higher the heat. Temperature is the average amount of heat in a specific room. And heat gets transferred 3 different ways. There is radiation, where energy travels across distance and space. We have convection. That's where the surface of this heats up and a current rises. So the hot air rises, or hot water in the form of a teapot. The hot air rises, cools, falls, and the cycle continues. This is convection. So this area gets warmed up by convection currents. So we have radiation, where it travels across distance. We have convection, which is a current, or we have conduction. Conduction is where you're touching. So if my tray was hot, I put my hand on it, conduction. If I touch it, it's conduction. If it's a current moving upwards, it's convection. And if it's traveling across space, like radio or electromagnetic waves from the sun, then it is radiation. It could also be from a fireplace, anywhere where the energy travels across distance. Not traveling up, that tends to be a convection current, and not when I touch it, conduction. So we have kinetic energy, this is the energy of motion, and we have potential energy. Potential, in your mind, you need to relate the word stored. It is stored energy. Energy is there, and it can be used or tapped into. So it can be changed into kinetic energy. Now I have a quick demo, so I'm going to kind of slide over here and magically pull a large fish tank out of thin air. Due to the magic of Hollywood, if you will. But here, so I've got a large fish tank here, and let's see if we can make our pinwheel move again. This time I am going to use my stored energy in the water, and lo and behold, making my pinwheel spin. It's stored energy. All I have to do is move the water from here down to here. As it flows downhill, it can go across my pinwheel, causing my pinwheel to move. I'm taking advantage of stored energy. And this is basically what we do using a dam. We're using hydroelectric energy. We're taking stored water and we're allowing it to flow downhill. It has potential to do work as long as we get it moving. So let me go ahead and get this out of the way. Kinetic, energy in motion, or potential can be used if we get it moving, in this case the water flowing downhill. Now, all these different forms are just ways that we can make use of it. Now let's talk about it in two other broad terms: renewable and non-renewable. Remember, when we talk about renewable, whether it's renewable resources or renewable energy, these things are replenished by a natural process in a relatively short time. Think human time scale, like a human's lifespan. If it can be recreated within a human lifespan, we tend to refer to it as renewable. If it takes longer than a human lifespan, then it becomes non-renewable. So renewable energy comes back all the time. Plants are a good source. Solar, wind, etc. These are renewable. They keep coming back and back. But then again, non-renewable. We can get them from resources that can be depleted, and they're not replenished by the natural processes within a human time scale. We can come up with a lot of different examples of that. But solar energy is really the number one, the big one. 99% of the energy that warms the earth and does all the processes of the planet comes from the sun. About 1% winds up being geothermal and some of our black smokers, life under the sea. But as far as what keeps the planet really going is the sun. But commercial energy, what you and I tend to use when I put on my hairdryer, this tends to come from non-renewable. This is energy sold in the marketplace, if you will. It can supplement the sun's energy. I mean, I can use lights to grow plants and other aspects, but 90% of what you and I are using just comes from burning fossil fuels, that oil, coal, things that we find in the ground that we dig up. Made by the planet, but it takes millions of years to create another batch, if you will. So once we use it up, it's not going to be back in our lifetime, or even greater humans, if you will. And when we talk about energy, we need to talk about it in terms of quality. We want high quality energy. Remember, the first law of thermodynamics, I can't create it or destroy it. I can only change it or transform it from one form to another. But when it gets transformed from one form to another, the second law of thermodynamics, I get a less quality of energy. It always goes from high quality to low. In physics, it's usually how it works. Things go from heat goes from hot to cold. In forms of energy, it goes from high energy to low energy. The rock on top of the hill, it rolls down. It doesn't go up on its own. It takes energy to do it. Things always go from high to low in the realm of physics. So we can start with high quality energy. Concentrated energy with a high capacity to do useful work. Let's look at an example here. We'll burn some alcohol as an example of it. So, a little bit here. This is an example of high quality energy. It burns with a high temperature, puts off a lot of heat. I can use this to boil water, create steam. In a sense, we use our gasoline, fossil fuels. We use it for the internal combustion engine to burn, to create those minor explosions which drive our pistons. High quality energy. And let's go ahead and get it out because it's literally getting me hot. So then we have low quality energy. Low quality energy has been dispersed and it has a low capacity to do useful work. Think about the ocean, if you will. Now, the energies come from the sun and it somewhat warm the ocean, but that energy is so dispersed, I can't really use all that energy to do much. It's a massive amount of energy, but it's so low at any given point. I can't use the ocean's water to actually boil anything or create a lot of heat compared to the burning of the alcohol. So high quality energy, the sunshine coming down, when it hits the ocean and begins to warm it, it becomes low quality heat. The energy gets dispersed. So these are low temperature, slower moving molecules. So has to follow these two laws of thermodynamics. The first law, energy can neither be created nor destroyed. So here I have potassium permanganate again, a similar one. I add in the glycerin, so I wind up and I'm going to get a chemical reaction. In this case, I'm not creating the energy. All I'm doing is transferring the energy already stored in the chemicals until a certain point that it will generate heat. But the first law, I can't create it or destroy it. I can only transform it from one form into another. And this one wound up catching my alcohol back on fire. The second law is that energy always goes from a more useful to a less useful form of energy. So now that I have burned the alcohol and given off the heat, once that heat disperses into the atmosphere, it's now low quality. It started off really hot, but it warms the whole room by a little bit. The fact that the whole room's a little bit warmer doesn't really, I can't utilize that energy. It goes from high quality to low quality energy. And that leaves us with energy efficiency, a measure of how much work results from the energy put into a system. The more we can improve energy efficiency, the more we can reduce waste. My electric car, it's about 130 miles to the gallon. If you convert the way the energy is done, directly gasoline compared to mine using electricity, it's the equivalent of 130 miles to the gallon. A lot more efficient than an internal combustion engine. So the more of those we have, we save energy. It's better that we can do. It is estimated that 84% of the energy in the United States is wasted. Now, about 41% of that is our first law of thermodynamics. As the energy gets converted, some is lost in the form of heat that we don't want, a waste energy, into the atmosphere around us. But unnecessarily, we're losing 43%. Once again, take a car that's getting 25 miles to the gallon, 25, 50, 75, 100, 125. It is 5 times less energy efficient than an electric car. Energy efficiency. The more efficient we can get as we can transfer energy from the plant, spinning the turbines, through the copper wires, into our room, into our home to use what we want, the more we can cut down on that 43%, which is potentially avoidable, the better off we'll be. Well, that wraps it up for section 2.3. Hope you enjoyed the lecture and our few demos along the way. Take care, guys, and we'll see you next time.